like to introduce Job Snijders, who will be presenting how to debug RPKI issues, overview of RPKI data structures and tooling. Now stick with me, this is a long introduction. Job is a principal engineer at Fastly, co-chair of the ITF Grow Working Group, co-chair of the RIPE Routing Working Group, vice president of PeeringDB, director of the Route Service Support Foundation, manager of the IRRD v4 project, member of the RIPE NCC Executive Board, and art director, most importantly, for the OpenBSD project. This is Job's 15th time presenting at NANOG. Job's first talk was NANOG was called NLNOG Ring, Network Debugging Never Was Easier, at NANOG 56 in Dallas 10 years ago. Welcome back to NANOG, Job. It's a pleasure to have you back with us today. Thank you.
Wow, that was a much longer introduction than I anticipated. I'm Job Snijders. Thank you for having me here. I first would like to express appreciation to the NANOG staff and NANOG volunteers. I think it's really cool you brought all of us together in this beautiful city. I've had a fantastic time the last few days, and I hope we will come back to Montreal at some future point. Today we're going to talk about RPKI debugging, and my agenda is as following. We're going to discuss what are RPKI signed objects exactly. In the presentation I'm sharing an overview of what kind of objects exist and what their function is, and give examples of human readable output. I'll cover a little bit how RPKI objects are discovered by RPKI validators, and cover how various timers in the system interact with each other. And then finally, there's of course room for questions, comments, remarks. So what's an RPKI signed object? You can use the Unix utility cat to view a binary blob, and if this is hard to read for you, you're not the only one. It is also hard to read for me. The RPKI signed objects are DER encoded binary strings that contain a number of digital sub-objects, and this is a departure from the model we had in, say, Whois or IRR. If you look at older technologies such as Internet Routing Registry, with command line utilities, you would see human readable text that is also mostly computer parsable. And with the RPKI system, we left that behind. We sacrificed the degree of readability, but we did gain cryptographic assurances. So signed objects are files on the file system, and the files are encoded following a serialization format that is formally notated in ASN1. And if you want headache or have trouble sleeping, that is the niche I would recommend you to go towards. Each of these files is identifiable by the SHA-256 of the file contents. RPKI objects are not malleable. And this is a great property because this allows RPKI objects to reference other RPKI objects, and we'll cover that later in the presentation. But also from an auditing and debugging perspective, it is a really cool property that each and every file in the RPKI is unique. The signed objects are structured according to the cryptographic message syntax, CMS. And CMS is what you can think of as an envelope. And on the outside of the envelope, you have hints about what the contents of the envelope are. And this allows software to layer by layer peel back these objects and parse them. So inside the envelope, there are two major components. There's the so-called E-content, or encapsulated content, and that's the payload of an RPKI signed object. So for instance, in the case of a ROA, the payload of the ROA is a single ASN that is authorized to originate a set of prefixes, and additionally, a set of one or more prefixes is listed. And those together form the payload. The rest of the object is the EE certificate that can be used to verify the cryptographic chain. The X509 EE certificate contains pointers to where you can find its cryptographic parent, what the key identifier of the parent is, what certificate revocation list applies to the object, and so on. Now, you can visualize the RPKI as a tree shape. The root is the trust anchor. And what we do with trust anchors is a thing called assumed trust. A trust anchor is a self-signed certificate, and each operator that deploys RPKI Origin Validation chooses which of the trust anchors they want to use in their network deployment. And in loading those trust anchor locators, you make a sort of a leap of faith that the operator of the trust anchor is acting in your best interest. Now, there are, if you view this in your mind as a graph, you have the root, the trust anchor. There are intermediate nodes. These are called certificate authorities. And then finally, at the edges of the graph, or the leaves, you have objects like ROAs, manifests, Ghostbuster Records, or BGPsec keys. And the arcs of trust that you follow towards those nodes at those leaves, that's called derived trust. So the procedure roughly is you have a trust anchor locator in hand. This is a small file that contains a URI and a public key. You fetch the certificate that is located at the URI. You can verify that it's the correct one by comparing the public key. And that certificate contains additional pointers where to find more RPKI information. So it contains a pointer to a manifest, to a CA repository, and so on. You download the objects behind those pointers. So you download the manifest. You open this manifest, you find a listing of files, and you download each one of those, and you verify all of these as you go. Now, in reality, validators will sweep in all the data in a bulk consumption fashion. So it's not that validators step-by-step walk through the tree and every time initiate a download action to fetch the next objects. But conceptually, this is how validators approach the RPKI tree. I made a beautiful drawing. It's not available as NFT. You can have it for free. And what I tried to express in this drawing is the pink lines is the discovery of aspects in this tree, and the black pointers are how you verify trust up to the trust anchor. So at the top you see and this pattern of a group of a certificate, a manifest, a CRL, and one or more ROAs. This small molecule or pattern is repeated over and over all through the RPKI data structures in the global RPKI database. So a certificate can be recognized by its SKI. This is the subject key identifier. You can think of this as the reference to itself. And the AKI. And the AKI is the hash of the public key of the parent of this object. And that tuple together is an important combination to start building a chain to validate objects. Now, a certificate also contains a pointer to a manifest. And a manifest is a listing of files that belong together. And the manifest itself also has an EE X509 certificate. So all these signed objects, the reason they're called signed is that all of them carry signatures that you can validate in a relationship to other objects in the RPKI ecosystem. The manifest has a SKI, a reference to itself. It has a pointer to what its parent is. it will point out what the certificate revocation list is that must be checked to confirm that none of the certificates in this small grouping of objects is revoked, and so on. So validators discover new objects following various pointers in the EE certificates, and then you walk back up the chain to validate whether everything is cryptographically intact. As I mentioned before, this tuple of the key pair identifier of the parent and the key pair identifier of the object itself, the AKI and the SKI, they are accompanied with information access extensions. So there is an authority information access extension that contains a URI where exactly the parent can be downloaded. And similar, there's a subject information access, which is a URI where on the internet the object is. So to confirm the validity of a given object, you have to also obtain the parent to see if the parent actually signed the object you're trying to validate, all the way up to the self-signed trust anchor certificates. So let's get into debugging. From the same group of people that brought you OpenSSH, LibreSSL, and OpenBGPD, there is a magnificent tool called RPKI Clients. And RPKI Clients not only runs on OpenBSD, but also on all flavors of Linux and Unix. It's very portable software. And RPKI Client is sort of the TCP dump of the RPKI technology stack. This slide shows how you can install RPKI Client on Debian Unstable. In yellow and black, you see what I type into the command line, and the white on black text is what the command line will likely show you. So step one is to just install the software using apt install RPKI Clients. It will pull in the required dependencies, and I do not recommend people to compile cryptographic software themselves. Make your life easier, use pre-packaged, pre-compiled distributions of cryptographic software. Do not compile things yourself. Anyway, you install RPKI Clients, you start it so that the process connects to the internet and fetches all the RPKI objects that can be reached through the trust anchor that you configured on the system. And once that's done, you can change directory into the so-called cache there. The cache directory is where the RPKI client utility on the file system stores all signed objects that it discovered and considered valid. The cache directory does not contain objects that are invalid. Invalid objects are moved out of the way or deleted. So if you're inside the cache directory, you can issue the command ls listing, and it shows you a number of directories. Each of these directories represents a RPKI publication point. I guess I cannot use the pointer around the corner, but if you squint your eyes a little bit, you can see in the upper right of the listing rpki.erin.net. And if you would change directory into that location, you would be inside Erin's RPKI repository and able to inspect all signed objects there. Now, how do you actually inspect an object? RPKI client has a command line option -F that stands for file mode. I hope I'm pronouncing that correctly. In file mode, you do not instruct the program to fetch all objects and validate everything, but you ask it to parse a single object and its parent and the CRL that is associated with it, and its parent's parent and the CRL that is associated with that, all the way up to the trust anchor. So instead of validating more than 100,000 objects, in file mode, you zoom in on exactly one object, and it will, in human readable format, print the encapsulated content and various other attributes of the EE certificate. And in the pink background is what signifies the encapsulated content. The white text on black background is what comes from the X509 EE certificate. And then the blue colored text is hashes. Earlier on, I mentioned that RPKI signed objects are non-malleable. And this property is important because each manifest contains a listing of files that belong together. And it lists a file name and the SHA-256 hash of the file contents. And this is how you can verify as validator whether you have the correct files together, or maybe you somehow ended up downloading a partial set. So manifests are of critical importance in the RPKI. It is a really cool innovation compared to the X509 framework on which the RPKI was built. And manifests allow us to detect replay attacks, because each manifest contains a so-called manifest number, and those can only monotonically increase. And this means that every manifest that you fetch, you can compare the manifest number, and you will use the higher one. And if a repository is presenting a manifest to you with a manifest number that is lower than what you already locally had cached, you know that the repository you're connecting to is malfunctioning. Replay attacks not only happen because evil hackers want to give you a bad day, but they can also quite easily happen if, for instance, a CDN cache delivery system is somewhat out of sync, and you ended up connecting to a node that has older RPKI data than the origin. So replay attacks can also happen by accident if the CDN, if there's a CDN in the middle, or some other apparatus that was intended to help distribution of objects, but somehow is malfunctioning. Manifests also help to detect whether the repository is providing you with a coherent set of objects and that they were not altered. Because the manifest lists the SHA-256 hashes of the objects that belong together. And if an object is corrupted through some way, maybe there's a bit flip, maybe there's gamma radiation from space doing something, you can confirm the SHA-256 hash of what you retrieved with what is listed on the manifest. And if they match, you know that you, up to each individual bit, have the correct file. It also detects you to, allows you to detect whether files have been deleted. So if a file is listed on a manifest, but in retrieving files from the publication point, either via RRDP or rsync, and for some reason you didn't receive information about that file, then you know that you have an incomplete set of data. And this brings us to that manifests are a robust mechanism to bundle ROAs together. Now, why is this important? If I create a ROA covering a /16, and additionally I create a ROA for, say, a /24 that I assign to a different ASN, I will be announcing the /16 from my ASN. The other entity is announcing the /24, a more specific of that /16. And if the two ROAs coexist and all validators have access to those two ROAs, both our announcements will be valid. But the moment, if for one reason or another, a validator only sees the ROA covering the /16, the BGP announcement covering the /24 will be considered invalid because it's RPKI invalid. And in such scenarios, it's better to discard both ROAs if one of the two is missing, rather than to proceed and use as many ROAs as you could get access to. So manifests are the mechanism to tell the world, use these ROAs together or don't use them at all. And that is what allows us to create very fine-grained ROA configurations that match up with the reality of our business. Let's take a look at another object that is used throughout the RPKI. CRLs, Certificate Revocation Lists. CRLs are used to tell the world, well, previously I signed so-and-so object, but that's no longer the case. You should, if you encounter that particular certificate, you should consider it invalid, even though it might not have expired yet, even though the signature matches up to the parent and the parent's signature matches up to their parent. CRLs are the mechanism to pull back, to signal to the world that the information that was previously distributed is no longer valid. There's thousands of CRLs throughout the RPKI ecosystem. On average, each CRL lists about 12 revoked certificates, and they also are a critical component of the integrity that RPKI can offer us. CRLs generally are short-lived because if you want to tell the world this is the list of things that no longer is valid, it of course makes a lot of sense that that list is periodically refreshed, and this is forced by setting the expiration time of CRLs fairly short, so in the order of, say, 8 to 32 hours. And this forces validators to periodically refresh between, say, once an hour up to once every 10 minutes, the CRLs to confirm whether things have been revoked or not. So CRLs are really what drive the sort of speed of the RPKI ecosystem, because I think those of you that have created a ROA, you generally see in the ROA web UIs that the expiration date is, I don't know, 10 years from now or 2 years from now. Those expiration dates are long-lived. CRLs are on the short-lived side. Another cool object that exists in the RPKI is called a Ghostbuster Records. Who are you gonna call? Ghostbuster Records exist to drop contact information in the RPKI system itself, so that if there is some kind of issue with a publication point or a set of signatures or objects, that it's like a business card inside the RPKI. And I've created a GBR record referring to my contact details, and I put this on my personal publication point. So if there's anything wrong with that publication point, you can look at my vCard and then send me an email, or maybe call me, or send me candy. Up to you guys. It might seem awkward to have vCards in the RPKI ecosystem in the current stage of RPKI deployment, because if there's an issue with an object on, say, rpki.aaron.net, obviously you're going to call Aaron, because the domain name is a strong suggestion where to go. But we're moving towards a world where a technology called publish in parent is used. And the mechanism is that the cryptographic operations happen on-premise, but the publication of the objects happens in the parent. So the cryptographic delegation is towards your own certificate authority that you run on your computing equipment. And once you've signed and created objects, you send them over to Aaron, and they appear on the Aaron server. So in such instances, you'll have objects that were not created by Aaron, but are hosted on the Aaron server. And for such scenarios, it is super useful if people leave behind business cards, because the location of the signed object is not a good hint who to call when there is an issue with the object. Additionally, new technologies are coming out of the IETF CyberOps group, such as resource-signed checklists. I'm going to tell you all about that in a different presentation, but it's a mechanism where we can use RPKI signatures to facilitate bring your own IP address movement into cloud providers. And those objects are distributed outside the RPKI publication system. So this means that the location of the object no longer exists in the sense that you cannot derive from the location identifier who the publisher is. And this makes it more important to keep dropping business cards over the place to help people understand who to contact if there is an issue with an RSC object. So there's not a lot of Ghostbuster records currently in the ecosystem. I may be the only person on the planet publishing them, but I encourage people to ask their RPKI service providers for Ghostbuster record publication capabilities, because I think this will greatly help in future debugging. Now, another application of the RPKI is route origin authorizations. And this is what a route origin authorization looks like on a more technical level. You point RPKI clients in file mode towards a given ROA file. It will print in the text on the black background information from the EE certificate. And in purple, you see the E content, the encapsulated payload. That is the meat of the ROA. So there will be a single AS identifier that is authorized to originate the prefixes that then follow. And for each prefix, there optionally can be a max length field filled in. So this is what a ROA looks like on a more zoomed in level. And every ROA contains expiration dates. The utility will show those as well. Finally, there is an object called the BGPsec Router Key. In the BGPsec model, every BGP update that you send to your neighbors, you sign with an ECDSA key. And the public component of those ECDSA keys you can publish inside the RPKI system, and those are called router keys. So by publishing the public key of the key pair with which I'm signing my BGP updates into the global system, all the world's routers can retrieve that public key to verify the signatures I put on the BGP updates. BGPsec is not yet super popular. Again, I might be the only person on the planet publishing BGPsec router keys, but I do encourage this community to investigate BGPsec and help the global deployment of this technology in the years to come. We're almost at the end of the presentation. What I want to cover is timers. If you contrast RPKI to IRR or WHOIS, IRR records do not have any expiration date. They are plain text blobs that can exist for decades on end. And this has happened in many occasions, especially in third-party databases. With third-party, I mean non-RAR operated databases like AltDB and RADB and NTTcom. And if once an object has been created in such a database, unless somebody removes it, it will be there forever and ever and ever until the heat death of the universe. Now, this is not possible in the RPKI ecosystem because each and every signed object contains an EE certificate, and every EE certificate contains a not before date and a not after date. And the not after date should really be considered like the expiration date on your carton box of milk. You don't want to consume spoiled milk. You don't want to use expired RPKI objects. Now, there's a lot of timers in this system. There is the not after on the EE certificate itself. There's the expiration time on the CRL associated with that particular EE certificate. The manifest e-content has an expiration date. Then the parent of all this has a not after. The parent has a CRL that has a not after, and so on. So if you look at a particular, a given ROA, there might easily be between 10 and 15 timers in play that dictate the validity window in which that ROA can be used. And since CRLs are on a relatively short refresh timer, those generally are what is called the transitive expiration moment trigger. And this means you gotta refresh RPKI data every hour. You gotta reissue RPKI signed objects maybe once a day. So it's a system that is hot. It requires constant re-signing. And I think this is a very good property of the system because the IR system, where there is no expiration timers whatsoever, has arguably led to issues. And this, to some degree, is mitigated in the RPKI ecosystem by associating expiration moments with everything. Quick references. You can find RPKI clients on the rpki-clients.org website. But as I mentioned, don't compile it yourself. Just install packages that come with your favorite Linux or Unix distribution. If you want to play with RPKI data in a way that is more accessible than the binary encoded rendition of it, there's a JSON file of about 130 megabytes that I refresh every few hours. And this allows you to inspect the current global RPKI database with Python or Node.js or whatever your favorite language is. And then finally, if you have any questions about RPKI or BGP or how BGP and RPKI interact with each other, email me, joe@fastly.com. And I'm also happy to help any parties that feel they're competitors, because it is together that we make the internet. So anybody can email me about RPKI. That's it for today. Thank you for your attention.
Okay, time for questions and answers. Anyone have any questions? We have one.
Hello, my name is Angel. I'm a security researcher for Beanfield. I just wanted to say that since yesterday, RPKI client has been pushed to backports, the recent version, and an older version is already unstable. So running unstable is not always recommended. I know it's probably just an example, but yeah, it's available in backports now, so it's way easier to install.
Angel, thank you for your comments. And I appreciate the efforts of the Debian community to make RPKI clients easily available to admins. Your comment reminds me of a recommendation that I want to express towards everybody in this room. Always run the latest version of the RPKI validator you've chosen. There never, ever is a valid reason to run an older version of an RPKI validator. Never. RPKI validators are security software, much like your browser, like Chrome or Firefox. And with security software, you have to run the latest version. It's kind of a race between attackers that could potentially give you a bad day by disrupting your RPKI system. and progressive insights from researchers or RPKI software developers themselves. But the latest version is what you have to run. And I recommend everybody to put like a recurring event in their agenda to at least once a month, the first of the month, confirm that what you're running in production is the latest release of the validator of choice. So when people ask me, what are you running? The answer is the latest version.
Thank you.
Any other questions, comments?
Hey, Guy Tall with Lumen Technologies. I had a question, maybe I misheard or misunderstood when you're talking about the manifests. I think it was slide 13 or 14. And you'd said that you had like a valid /20 and then an invalid /24. And in that situation, both the 24 and the 20 would be withdrawn. Did I mishear that or misunderstand what you were saying?
The example is 2 BGP announcements, /16 coming from AS1, /24 coming from AS2. And because the /24 is a more specific of the /16, if you want to create ROAs, you have to create 2 ROAs, because per ROA you can only list 1 origin AS. So you have to create a ROA for the /24 and one for the /16.
Okay.
And you have to consider them both because if you have one of the two, if you only have the ROA covering the /16, you might consider the /24 invalid. So you need both ROAs together to have both BGP announcements be considered valid. And what manifests allow you to do is to confirm that you have all the ROAs that belong together, that you actually have all that belong together. And if one of them is missing, you would not consider any of the ROAs listed on that manifest, which would mean that the routes flip to not found, which is preferable to routes flipping to invalid, simply because a few objects were missing from the publication point. So I hope my reiteration helped clarify, but I'm also happy to send a link to the NANOC mailing list with a blog post I wrote a while back that instead of me verbally trying to explain what it does, writes down in text how manifests work and why they are important.
Well, yeah, I mean, I guess if it goes to, not found versus invalid, that's better. But the question just is, does that open up a vector of attack where somebody can try to create a /24 knowing it's invalid and then go and, knock the validity off of, SuperNet that's, covering it?
I'm not sure we have enough time to go through this example, but the way RPKI is structured and why manifests are important is to resolve issues like this and to prevent attackers from being able to flip otherwise valid announcements into invalid. So one example is if an attacker sits between you and the repository somehow, a man-in-the-middle attack of sorts, and hides a few objects, or a CDN somehow is only passing on an incomplete set of objects, the manifest allows you to confirm the completeness, and in doing so, you can avoid that /24 being rendered invalid because the ROA was hidden, because the manifest allows you to detect that ROA is missing. Yeah, let's take it offline.
Yeah. Yeah, no, wearing a white hat, yeah, that definitely makes sense. But wearing a black hat, I'm like, I could kind of cause problems with that. So I don't know, but it sounds like it's a more complicated answer. So we'll talk later.
Yeah,
Okay.
in RPKI context, the answer often is it's complicated.
Okay, we have time for one more question.
Rob Robertson with Zayo, and I've been trying to push out RPKI onto our network for a little bit, and I want to get to the point of like running the latest versions. We have been running the latest versions of like the RTR software from NL Labs and encountered a bug where all of our Nokias stopped loading their databases. So there's a little caveat with running the latest software. And the second question I have is validator diversity. Is there any benefit to possibly running the Fort validator and the Routinator together, and then having that serve as the basis of your truth, and then having a caching server and then feeding your routers?
It's complicated.
It is.
Diversity is a very, very interesting topic to study, because in a system like RPKI, the system is as strong as the weakest link in the chain. So if you're running Routinator and RPKI client next to each other, and an exploit is discovered in Routinator, it somewhat nullifies the efforts of the other validator. But on the flip side, if the RPKI client developers, make a mistake, a bug is introduced, maybe it takes a few days to fix. Meanwhile, you have the other system, and it's much like, are you running a network where you use both Cisco and Juniper for either negotiation power or resiliency to? But you also know that there's a cost associated with that, because your staff needs to be familiar with both systems, both UIs, both support chains, and so on. So it's really a per organization decision that you must make, whether you trust the validator to the degree that that's the only one you use, or that you want multiple different implementations from different teams. I don't have a best current practice to share with you. I think this is something people must consider themselves. I can say, however, always run multiple validators.
Oh yeah, that's a given.
So if, like in Fastly, we use multiple validator instances from a single vendor, but that part is critical. Don't run with one instance. Make sure you have a few instances, and whether you want them to be diverse or not, that's a consideration.
And geographically diverse.
Yep, absolutely.
Thank you.
Thank you.
Great. Thank you very much, Joe.